This is a Softrock Ensemble. There is no modification whatsoever in this unit, and I will now show some evaluation of it with particular interest on the spurs that may come out from this unit. There has been discussions on the Softrock 40 group about this and the mechanisms, so I am going to be very pedantic on what I'm showing here. First of all, instruments have to be calibrated. I have a cable from input to output, and I calibrate this thing to show zero attenuation, zero, and regardless of frequency. This is trivial. This is a resistive power splitter combiner, 7 ports, and I have connected it, and I look at the attenuation, and you can see it's 15.3 dB from maybe 8 megahertz up to at least 100 megahertz. Then attenuation increases as I go up to higher frequencies, but not so much. The lowest frequency I can get is 0.3 megahertz, and there the attenuation is higher. I don't know why, but it's 15.9. So in the evaluation, you can see at 5 megahertz it's 15.5. But I'm going to test this unit at 14 megahertz, and 15.3 is fairly accurate. The Softrock transmitter will produce about 1 watt, and that's too much for this combiner, so I will use it together with this set of 2 3 dB attenuators, and I need to know the attenuation from this point to any of the outputs of this splitter combiner, and I can see that here, and you can see here 21.4 dB at 12 megahertz, and 14 megahertz it says minus 21.3, and it stays constant up to, well, it's reasonably close up to 100 megahertz and down to 300 kilohertz. So I can take 21.3, that will be accurate for the measurement of the output power. And we know then now that the response is reasonably flat, and the impedance is close to 50 ohms, as you can see. This is the transmit side of Linrad, and you can see the transmitter is right now off, and this is a SDR IP, and I have set the leak through of the oscillator on the Softrock to be at the center of the spectrum here, and I also set the spectrum analyzer here, so you can see the leak through. The level of that is minus 48 dBm, so it is a weak signal. And I enable the transmitter at full power by clicking here. And then what happens is this. We have the main signal, the mirror, the strongest spur, which is not quite 40 dB below the strongest signal. Then we have something here which is 50 dB down, and something here which is, well, another 15 dB or so. On the spectrum analyzer it looks like this. peak surge marker, you can see that the power is 8.8 dBm. So, according to previous calibration, this should be 1 watt. The oscilloscope tells me it is 1.59 volts, while 1 watt should be 1.72. So the level is a little bit below 1 watt, but yet the spur is a little bit too strong compared to the -43 that is in the rules. I can inject a second signal into the microphone input like this, and you see now I have a two-tone test, and here are the two tones, the mirror and the spur, the -3 times the modulation frequency spur. Have a look at this when I turn the level up and down of one of the signals. I turn one of them down until it's disappeared, and you see which one is still present, and I bring it back and I turn the other down, and you see the other one is present. It's the outer one, and it's the other outer one. They go down in amplitude when I have two equal tones, but they are both there. And the mathematics of this is quite simple, and you can find it on the Softrock mailing list archives, how this works. I can turn the frequency and you see how things behave. Well, I have to stay within the passband. The spectrum looks ugly here with the SDR IP, because it's a real receiver with good sensitivity and good dynamic range. So signal intermodulation on both sides, mirror image, and I can turn that up and down with the balance control I have here. So you can see it's really that phenomenon. Well, something like that. And then we have false signals and their intermodulation products. And we have this strongest spur, which is now, is it 10, 20, 30, 40, 39 dB below the main signal. And some more. When I look at the spectrum analyzer, it looks like this. And you may think this looks much better, and indeed it does. And I have to have some more light probably to see this better. So the strongest spur here, 40 dB down, other stuff at -50, and then the rest is small. I will now reduce the power by 10 dB. I put 10 here for attenuation. And then what happens is fairly dramatic. The strongest spur is the mirror image, which I could balance better. The offending spur at 3 times the modulation frequency on the opposite side is now much weaker. 10, 20, 30, 40, 50 dB or so. So non-linearity in the amplifiers is a problem with the Softrock. And you can see here, amplitude, it looks quite good now. So a power amplifier on top of this would be a good thing. Maybe not too much power, but more than 1 watt would be okay. I'm now feeding the output of the Delta 44 that I was previously using to feed the Softrock. Now I'm feeding it into the sound card of this computer, the motherboard sound card, and you can see the mirror image balancing doesn't fit perfectly here, but you don't see the overtones. And this is at 10 dB reduced power, and I go up to full power. Oops. This does not look so good, so I have to do something about it. Well, what I had here, I turned the microphone down to 0, and it's a little bit better, but this is probably not the Delta 44, it is the microphone input on the motherboard sound card of this computer. So I can verify this, and I have done that, and the problem is not due to the sound card. Well, what I had here, I turned the microphone down to 0, and it's a little bit better, but this is probably not the Delta 44, it is the microphone input on the motherboard sound card of this computer. So I can verify this, and I have done that, and the problem is not due to the sound card. I added an audio attenuator, and you can see a little bit of intermodulation down here and down here, and that is probably the motherboard sound card and not the Delta 44. And then we have some noise, that's because of the sloppy connection with earthing and other things, I think. Anyway, the wide spectrum that is visible on the 7 MHz band is due to the Softrock and not due to the audio signal feeding it. I have put 2 turns on T2 to look at the output from the mixer. I have also put a series resonator parallel to, what was it, C21, to see what frequency is involved in the strongest intermodulation, the strongest spur. What I see on T2, as you can see here, the main signal is here, minus 10 dBm. Then, minus 10 dBm on 7 MHz, and then minus 50, that's 40 dB down on the second harmonic. And the third harmonic, which is not an harmonic, it's the regular first order mixer product, because the LO has a large content of the third harmonic, because it's a square wave. It's at minus 19 dBm, that's 9 dB below the main signal. And then the fourth harmonic is a little bit weaker, but not much, or maybe identical to the second harmonic. And so on. This is from DC to 200 MHz. All the overtones are strong, and at higher frequencies the second order are not so different from the third order harmonics. Or, sorry, the odd orders and the even orders are not so much different in amplitude at higher overtones. I have placed a tunable series resonator with this capacitor and an inductor across C21, and I'm taking out the voltage across C21 through a 220 ohm resistor into the spectrum analyzer. And I have here set the SDR IP on the spur frequency, and I have set the S meter to show the graph of the signal level, and I will tune this resonator and look at the spectrum analyzer while doing so. Here you can see I am on the, what is it, 3rd, 5th, 6th overtone, and that has a very small, if any, effect. And then I go further. So this is the 5th overtone, and I can attenuate it significantly. And if it has an influence, that is a small influence. Then I continue. Sorry, wrong direction. Here I'm removing the 4th overtone, and it has a small effect. But if I turn further on, the signal goes down more. So this is probably not the 4th overtone, it's that I'm starting to affect the 3rd overtone here. I have to change the inductor. And now I tune again with this new inductor. And here we have the 3rd harmonic suppressed. And indeed it makes a big difference. It's about 10 dB. But when I tune here for the best suppression, I can reach a little bit better, but it's still well suppressed, the 3rd overtone. I don't know about the details of that, but probably the level into the next stage is not quite the same as the level across this C21 capacitor. There are some other couplings of this signal on the circuit board, probably. And now I continue downwards. And here the 2nd harmonic is significantly weaker. But you can see the level is the same. At the end I had some effect on the 3rd harmonic. So math tells me that the product comes from mixing of the 2nd harmonic and the 3rd harmonic, but the 2nd harmonic does not come from the mixer. So it is generated in subsequent amplifiers, means that the product is a 3rd order, 2 times the fundamental plus the 3rd order. That's the reason for this spur. So one way of getting rid of it is to put a filter that removes the 3rd order, the 3rd overtone out from the mixer. And that means this 7 megahertz, I'm running it on 7 megahertz to make the problem stand out as much as possible on this box, which is designed for 7, 10 and 20. Sorry, 7 megahertz, 10 megahertz and 14 megahertz. The other solution would be to improve linearity of the subsequent amplifier, if we want to make this a broadband transmitter. The signal is still 1.59 volts on the oscilloscope, and on the spectrum analyzer I have connected it back. It says 8.6 dBm. So the power is the same, but at this time the spur is weaker. It is suppressed by more than 40 dB now, but it was less than 40 before. The reason is I was looking for intermodulation by use of a small magnet. And if I move this magnet here close to the transformer, you can see something happens to this intermodulation product. And also, if I move it close to the output transformer, it does have some influence. It decreases the intermodulation, but I can find position. Now I am on the input transformer. And you can see that the output power is a little bit affected when I couple too much, but then the spur becomes very strong. So there is a contribution from the transformers, but probably the most important part is the linearity of the semiconductors.